Hey everyone, welcome back. Ready to take a deep dive into some pretty mind-bending physics with me today.
It's always up for a challenge.
We're going to be tackling Majorana particles and something called topological order,
Okay.
and how all of that ties into the world of quantum computing.
Sounds fascinating.
Yeah, and to guide us on this journey, we've got a couple of Wikipedia articles to pull from, one on quantum computing and the other on topological order.
Great starting points for sure. Those articles are like our trusty maps to navigate this complex landscape.
Definitely. All right, so before we get too far into those crazy Majorana particles, let's set the stage a little bit.
Okay.
For folks who might be new to this whole quantum thing, what exactly is quantum computing?
Well, at its core, a quantum computer is a totally different beast from the classical computers we use every day.
So not just a souped-up version of my laptop.
Nope, not even close.
Yeah.
It leverages the strangeness of quantum mechanics to tackle problems that would make a classical computer go
What?
just completely stall out. I mean, we're talking problems that would take millions of years to solve.
Okay, so what's the secret sauce? What makes quantum computers so powerful?
Well, think about this. In the quantum world, particles can act like waves, and they can exist in multiple states at the same time. That's called superposition.
So it's not just a bunch of ones and zeros like in my computer.
Exactly. Instead of bits, which are either a 0 or a 1, we have these things called qubits.
Qubits.
Yeah, and a qubit can be both 0 and 1 at the same time. That's wild.
That's wild. So instead of flipping a coin and getting heads or tails,
Right.
a qubit is like getting both.
Exactly. Like the coin is spinning forever, in a way.
So with all these possibilities happening at once, it's no wonder people are so excited about the potential of quantum computers.
Oh, the potential is huge. Drug discovery, material science, breaking encryption. The list goes on.
It almost sounds too good to be true.
Well, there's a catch. You see, building these quantum computers is incredibly challenging.
How so?
Well, one of the biggest hurdles is something called decoherence. Decoherence.
Yeah, imagine you're trying to build a house of cards,
Okay.
but there's a hurricane raging around you.
Oh, no.
That's kind of what it's like trying to keep these delicate quantum states stable enough to actually do computations. Any tiny disturbance from the environment?
Like a little vibration or a change in temperature?
Exactly. That can mess everything up. So we need ways to make these quantum states more robust, more resistant to decoherence.
And that's where our mysterious Majorana particles and this topological order come in, right?
You got it.
Okay, so let's start with Majorana particles. What are they, and why are they so special?
Well, these particles are fascinating. They were actually predicted back in the 1930s, but we're still working on conclusively proving their existence.
So we're not even sure they exist yet.
We have good reason to believe they do, but it's a tricky business pinning them down. What makes them unique is that a Majorana particle is its own antiparticle.
Wait a minute. It's a mind bender.
Its own antiparticle. What does that even mean?
So every particle has an antiparticle, right? Like the electron has the positron. They have the same mass, but opposite charge.
Right.
But for a Majorana particle, there is no distinction between the particle and its antiparticle. They're one and the same.
That's pretty wild.
It is. And these elusive particles are predicted to pop up as what we call quasi-particles in systems exhibiting something called, you guessed it, topological order.
Okay, two new terms in one sentence.
Right.
Quasiparticles and topological order.
Yeah.
Let's start with topological order. What in the world is that?
Okay, imagine you have a bunch of particles, right? Not just sitting there, but all interconnected in a very particular way.
Okay.
Interconnected on a quantum level, that's what we call entanglement.
Entanglement.
Yeah, and the patterns of this entanglement, how these particles are all woven together, well, that creates what we call topological order.
So it's not just about where the particles are in space, but how they're related to each other.
Exactly. It's like a new way of classifying matter, not based on its physical arrangement, but on these intricate patterns of quantum connections.
So different patterns of entanglement create different types of topological order.
Precisely. Think of it like phases of matter, but instead of solid, liquid, and gas,
Gotcha.
we have different types of topological order.
And these Majorana particles, they somehow emerge from this topological order.
That's the prediction, yes. They exist not as fundamental particles, but as quasi-particles, collective excitations of many particles that behave like a single particle.
That's a mouthful.
I know, right? But the exciting thing is that because they're tied to the topology of the system, they are incredibly stable. Much more so than traditional qubits.
So they could be the key to overcoming that decoherence problem we talked about.
Exactly.
Right, I'm starting to see the connection here, but how do we actually use these topologically ordered systems to build a quantum computer. What does that even look like?
Well, that's where things get really interesting. We're talking about braiding information into the very fabric of reality. But to understand how that works, we need to dive into the concept of topological quantum computing.
Oh boy, this is getting deep.
We're just getting started.
Okay, so braiding information into reality, huh? That sounds pretty intense.
Well, it's pretty mind-blowing stuff when you think about it.
Yeah, so how does that actually work, and where do those majorana particles fit in?
It all boils down to this concept called topological quantum computing.
Okay.
Now, in a regular quantum computer, the information is stored in the state of those individual qubits.
Right, those qubits that could be 0 and 1 at the same time.
Exactly. But in a topological quantum computer,
Yeah.
we do things a little differently.
Okay, how so?
Instead of storing information in individual particles, we encode it in the topology of the system.
And the topology, you mean like those patterns of entanglement we were talking about?
You got it. We're essentially weaving the information into the very fabric of how those particles are connected.
Okay, so instead of fragile qubits, we're using the topology of these entangled particles to store information.
Precisely. And because the information is embedded in the overall structure,
Yeah.
it's incredibly stable, much less susceptible to those pesky environmental disturbances that cause decoherence.
So it's like those knots in a rope, even if you shake it,
Right.
the knot stays put.
Exactly.
It's pretty amazing to think that something as abstract as topology could be the key to building more reliable quantum computers.
It is, isn't it? It's like we're harnessing the power of pure mathematics to create something incredibly practical.
So is anyone actually working on building these topological quantum computers?
Yeah.
Or is this still purely theoretical?
Oh, no, this is definitely an active area of research. There are some brilliant minds out there trying to make this a reality.
Really? Like who?
Well, companies like Microsoft are investing heavily in topological quantum computing research.
Wow, Microsoft. I guess they're always looking for the next big thing.
They are, and it's not just about the big tech companies either. There are a lot of universities and research labs around the world exploring different approaches to topological quantum computing.
So it sounds like there's a real race to make this technology a reality.
In a way, yes, but it's also a very collaborative field with a lot of shared knowledge and open research. Everyone's working towards the same goal.
I see. So it's not just about competition,
Right.
but also about collaboration.
Absolutely. It's a really exciting time to be in this field because we're constantly seeing new breakthroughs and discoveries. It feels like we're on the cusp of something truly revolutionary.
Okay, I can definitely feel the excitement,
Yeah.
but let's step back for a second.
Yeah.
We've been talking about how this topological quantum computing could solve problems and revolutionize industries and all that.
Right.
But are there any downsides? Any potential challenges we need to be aware of?
Well, as with any emerging technology, there are bound to be some hurdles along the way.
Okay, like what?
Well, for one thing, actually finding and manipulating these Majorana particles is still a major challenge. Remember, we haven't even definitively confirmed their existence yet.
Right, right. So we're trying to build a computer based on particles that we're not even 100% sure exist.
It sounds crazy when you put it like that, doesn't it? But that's often how science works. We explore the unknown, push the boundaries of what we know.
And sometimes that leads to incredible breakthroughs.
Exactly. And besides that, there are other engineering challenges to overcome too, like figuring out how to scale up these systems.
So we can build bigger, more powerful quantum computers.
Exactly. And then there are the theoretical challenges too.
Like what?
Like developing new algorithms that can actually take advantage of the unique properties of topological quantum computers. It's a whole new way of thinking about computation.
So it's not just about building the hardware,
Right.
but also about developing the software to run on it.
Exactly. It's a multifaceted challenge that requires expertise from different fields: physics, computer science, material science, engineering.
So it's a real team effort.
It is, and that's what makes it so exciting. It's a convergence of different disciplines all working together to push the boundaries of human knowledge.
I gotta say, you've really painted a fascinating picture of this whole topological quantum computing thing. My brain is definitely doing some quantum gymnastics trying to wrap my head around it all.
It's a lot to take in, I know.
Yeah, but it's amazing to think that we could be on the verge of a technological revolution driven by this mind-bending physics. It makes you wonder, what else is out there? What other mysteries are waiting to be uncovered?
Well, that's the beauty of science, isn't it? There's always more to discover. And who knows, maybe one day we'll be having a deep dive into something even more mind-blowing than topological quantum computing.
I can't wait. It's pretty amazing to think about how much we've learned,
Yeah.
by digging into these Wikipedia articles. Who knew they could be so fascinating?
Right. Sometimes the most unexpected places can lead to the most incredible journeys of discovery.
That's for sure. I feel like my brain has been on a real adventure today.
Right.
We've gone from, like, the basics of quantum computing to this whole idea of
Yeah.
braiding information into reality with these majorana
It's
particles.
pretty mind-blowing stuff.
It really is. So as we wrap things up here, what would you say is the biggest takeaway for our listeners?
Mm. Well, I think the most important thing to remember is that we're just scratching the surface of what's possible.
With quantum computing?
With quantum computing, with these new ways of understanding the universe, with everything, the future is full of possibilities, and who knows what incredible discoveries await us.
It's exciting and maybe a little daunting at the same time.
Oh,
Yeah.
absolutely. But that's the beauty of exploration, isn't it? There's always something new to learn, always a new challenge to tackle. It's what keeps us moving forward.
So true. So for anyone listening who's feeling inspired to learn more, where should they go? What resources would you recommend?
Well, there's a ton of great stuff online these days. You could check out websites like the Quantum Computing Report or the Institute for Quantum Computing. They've got some great overviews and insights into the latest developments in the field.
Awesome. And of course, there are always books for those who like to really dive deep.
Yeah, Quantum Computing for Everyone by Chris Bernhardt is a good one.
Okay, I'll check that out. And I know there are also a lot of online forums and groups where people are discussing this stuff all the time.
Definitely. There's a whole community of quantum enthusiasts out there. It's a great way to connect with other people, ask questions, and
Yeah.
share your own thoughts and ideas.
It's amazing to think that we can all be a part of this journey of discovery, even if we don't have, like, a PhD in physics.
Absolutely. Science belongs to everyone, and curiosity is the only prerequisite.
Well said. Well, I think we've covered a lot of ground today, from the
Yeah.
very basics of quantum computing to those wild Majorana particles and the mind-boggling implications of topological order.
It's been a real deep dive.
It has. And who knows, maybe one of our listeners will be the one to make the next big breakthrough in this field. So to everyone out there, keep exploring, keep asking questions, and never stop being curious about the universe around us.
I couldn't have said it better myself.
Thanks for joining us on this deep dive into the quantum realm.
It's been a pleasure.